Okay, so let's continue. Okay, so that's the condensed matrix. But when we try to develop a method used for the computer, there are some special considerations. Like we like to develop a method which can be applied to all elements. So if we can use the static condensation for this element, the element stiffness matrix, which is only a 5 by 5 matrix. But for all other elements, the element stiffness matrix, which is a 6 by 6 matrix. So it will be a special conditions. And for your homework problems, you will get a 4 by 4 element stiffness matrix, which is another special case. But how can we get the same results for all the elements? So okay, so that's what we can do. We will add a row of 0 and a column of the 0 to change the condensed matrix back to the 6 by 6 matrix. And here will be the theta A. Usually we will write the theta A and the theta B. But you can say the theta A, it is not the common definition of the theta A. Usually the theta A will be the this is the theta B. Okay, since if we like to consider the member end force related to the deformation of this element, the important things will be the rotation for this element. Okay, but if we use the static condensations, the original theta A will be eliminated. Okay, so the original the theta A is eliminated, so you cannot find the okay. So originally we need two rotations for the joint tool. One is the column top end rotations. The other one is the beam, the left end of the beam, the rotation of. And if we use the symbol, it will be the theta 2, comma 1, theta 2, comma 2. So since we have two different rotations at this joint, so we need to use two symbols. Okay, so if we choose the element 2 to do the member end release, or if we use the static condensations, the element 2, we will develop the 5 by 5 condensed matrix. But I just say we like to get a common rule for all elements. We do not like to treat the special case for. Okay, so then we can add a row of 0 and a column of zeros back to the element stiffness matrix. If you check the reference book, also you can see a theta A put here. But you can say the theta A, since for these two rotations, we can choose condense this one. if we choose the theta 2 to be eliminated, so we can condense it by the static condensations. Usually, if we got two rotations, you can condense out only one. You need to keep one. You need to keep one rotation to the final. So in these problems, if we keep the theta 2 1 to the global displacement vector, you can say here will be the theta A for the remainder degree of freedom. Okay, so right now, if you add a row of zeros, the theta A you saw here, you can say that's the theta for the remainder degree of freedom, just like I'm sorry, there is a okay, since I use my cell phone to record the video, there is just an incoming call, but I didn't answer that. Okay, so the theta 2 1 is the one to be remained in the global U vector. The theta 2 2, that's the element stiffness matrix for the one we are calculating right now, but we eliminated this one. When you add a row of zeros and a column of zeros back to the element stiffness matrix, you can say the theta will be the remainder degrees of freedom. And for the member end force for the element 2, the member end force of the element 2, they are related to the end displacement of this of the element 2 only. So the remainder rotation, the remainder degree of freedom, which is not related to the member end force of the element we are considering right now. So that's why we need a column of the zero. The column of the zero represent the remainder degree of freedom since it is the rotations of other member. So it is not related to the member end force of this element. Okay, and also the row of the zero, it means the other end displacement of this element, which will not contribute to the end bending moment of the other elements. Okay, so that's usually what we will do. Add the zeros back, and it is only the only advantage of this is we can restore the common rule for all elements, since right now the element we consider the static condensations, the dimension of the element stiffness matrix is still the 6 by 6. It is still a 6 by 6 matrix. Okay, the static condensation can be applied to many problems, not only for the member end release, and actually it is a very effective method to develop a very efficient program. For example, for these problems, we got element 1, 2, and 3. And if we calculate the element stiffness matrix, and assemble it to the global K. Okay. And right now, in the global stiffness matrix, we got only the end force related to the member 1 only. But then later we can calculate the element stiffness of element 2 back to the global. Also, we assemble this element stiffness matrix into the global K. And right now we can got I will say it is a temporary global K matrix. Since for the complete global K matrix, you need to assemble all these 3 elements. If you added all these 3 elements into the global K matrix, then you can say you got the complete global K matrix. But if we added only 2 elements, stiffness matrix into the global K matrix, so you can say it is only the partially assembled global K, or you can say that's the temporary global K. For the temporary global K matrix, you need the nodal degrees of freedom. Okay. Since for the element 1 and the element 2, we need to use the nodal degrees of freedom for the joint 1, for the joint 2. Also, we need it for the joint 3. For the element 1, we need to assemble the small K matrix into the global K. We need the nodal point 1 and the nodal point 2. And for the element 2, when we assemble the element stiffness matrix into the global stiffness matrix, we need the nodal degrees of freedom for the nodal point 2 and the nodal point 3. Okay, so for the partially assembled K matrix, we need only 9 degrees of freedom. And if we can change the dimensions, the global K matrix will be only a 9 by 9. Okay, so for these 4 degrees of freedom, we can use the static condensations even for a partially assembled matrix, even for the partially assembled global K matrix. Since we know for the nodal point 1, nodal point 2, we do not have, let's check these 3. Since we have assembled the element 1 and the element 2 into into this global K matrix, so the right hand side will be the sum of member end force. Okay, so right now the right hand side of the force vector it includes the contributions from the element 1. It has the contributions of the member end force from member 1. Also, it has the contributions of the member end force from the element 2. And if we check the structures, the joint 2, there are only 2 elements connected. There are only 2 elements connected to the joint 2. So if we have already summed up the member end force for member 1 and the member 2, so for these two, it will be equal to the applied nodal load at joint 2. Okay, so if we assemble the member end force of member 1 and the member 2, then the summations of these two member end force will be equal to the applied external loads at the joint 2. Okay, that's the equilibrium. If we check the equilibrium equations at the joint 2, oh, I'm sorry. Okay, hang out the phone again. So for the joint 2, we have assembled the element 1 and the element 2. Then we know the right hand side force vector should be the applied external loads at this joint. And if we consider the member loadings, so it could be the calculated equivalent nodal loads. Okay, so if we assemble the element 1 and the element 2, then we can say we know the right hand side elements for these 3 degrees of freedom. Okay, so you can say we have 3 static conditions. We got the 3 static conditions. Since we know the 3 corresponding elements in the right hand side force vector. Okay, so we got the 3 static conditions. Okay, so we got the 3 static conditions. Since we know the assembled global stiffness matrix, which has we know the 3 elements in the force vector. We know the 3 elements in the force vector. Okay, so we got the 3 static conditions. So at this step, we can do the static condensations. No need to wait for the complete global stiffness matrix. Even we assembled only 2 element stiffness matrix into the temporary global K matrix. But since for this temporary global K matrix, we got the 3 known static conditions. So we can do the static condensations. Okay, so we can do the static condensation for the partially assembled K matrix. For this partially assembled K matrix, we got the 3 known conditions. So we can do the static condensations to eliminate the 3 corresponding degrees of freedom. Then we can assemble the group K matrix, which will be a 6x6 matrix only. We can eliminate the joint 2. And even for the joint one, we can also, since for the joint one, it is the nodal degrees of freedom related to the boundary conditions. So you can use the basic method to handle the rigid joints. Also, then you can eliminate the three degrees of freedom. But the reason why we can eliminate the three corresponding degrees of freedom for the node point 1, it is not related to the static condensation. They are related to the known boundary conditions. Since we know the nodal degrees of freedom or the nodal displacement for the node point 1, they are equal to zeros. So we can eliminate the three corresponding columns. And the three rows of the equations, they are related to the unknown reactions. Since we don't know the right-hand side force vector, we don't know the elements in the force vector, so we don't need to keep the equations. Okay, so we can eliminate the three rows and the three columns based on the known boundary conditions. But although they are not based on the static condensations, but we can eliminate. So if you consider the boundary conditions right now, you can even eliminate the 3 degrees of freedom for the nodal point 1. Okay, so that's the what we can do right now. So I will take a break here.